Okay, this is part 2 of lesson 7.4, proving trig identities, and we're going to prove a couple more challenging identities. In this first example, we're going to prove it by working with fractions. In the second one, we're going to prove it by factoring, and then I have a factoring proof for you to try on your own. So let's get started here. We're going to start with the left side of our identity. The left side of our identity is this fraction here that we're going to work with. Tan squared x plus 1 over cosecant squared x minus 1. In order to work with these, or work with this left side, we need to have some familiarity with the Pythagorean identity. So I'm going to put that up here real quick. Our Pythagorean identity. There's the sine x square or sine squared x cos squared x equals 1 version, but then there's also these two secondary versions. The first one says that 1 plus tan squared x equals secant squared x, and it's valuable sometimes to take two terms and condense them into one term. And then the other version says that 1 plus cotan squared x equals cosecant squared x. So let's look at what we have here. We have tan squared x plus 1 in our numerator. Well, if we look at the second version of the Pythagorean identity, we have 1 plus tan squared x, which we could write the other way and say tan squared x plus 1, but either way, tan squared x plus 1 is equivalent to secant squared x. So that's going to be our first step. We're going to make a replacement in our numerator and call it secant squared x. Our denominator is also a version of the Pythagorean identity. But instead of 1 plus cotan squared x, we actually have cosecant squared x minus 1. If we look at this identity, we can rearrange it by subtracting 1 from both sides. And we end up with cotan squared x equals cosecant squared x minus 1, which is in fact what we have on the bottom here, cosecant squared x minus 1. So we can replace that with just cotan squared x. And now we have secant squared x over cotan squared x. The right side of our identities, we have a secant squared x in the numerator, right? Because there is no denominator here, so that's in the right spot. So the only thing we now have to change is we have to find some way to change cotan squared x into tan squared x. Fortunately, we have a relationship that shows that those two are identical. Not identical, but related. And that's the reciprocal identity. Cotan squared x is equal to 1 over tan x. So what that also means is that cotan squared x is identical to 1 over tan squared x. Okay? Even to degree 1, degree 2, the relationship remains the same. So we have another identity that we can use here. We can replace that cotan with 1 over tan squared x. How do you divide fractions? Well, you invert and multiply. So instead of secant squared x divided by 1 over tan squared x, flip this fraction and multiply it. So flipping that fraction, we get tan squared x over 1. I'm not going to write over 1 because it's just tan squared x, and we're multiplying instead. So there we go. We have demonstrated that our left side is equivalent to our right side. Therefore, we have proven the identity. All right, let's try factoring. Everyone's favorite. In this example, we have a left side and a right side. If we look at our right side, we could do a little bit of factoring over here because in the numerator we have two common terms, or a common term here. But if we look at our left side, we actually have something unique. Secant to the exponent 4x minus 1. If you were to consider secant 4x minus 1, and you were to say, hey, let's let y equal secant squared x. Well, then all we would have here is y to the exponent 4 minus 1. Y to the exponent 4 minus 1 is a difference of squares. To factor a difference of squares, you take the square root of the first term, so y squared, square root of the last term, 1, and create two factors, one with a negative sign, one with a positive sign. So we've just factored this difference of squares, but if y is secant, well then really what we have here is we have secant squared x minus 1 and secant squared x plus 1. So by factoring a difference of squares, you can factor this trig difference of squares. So I'm going to do that. The square root of the first term is secant squared x. Square root of the last term is 1, so we got secant squared x minus 1 and secant squared x plus 1. So we have factored this difference of squares. Now we have another difference of squares here. Or, if you look at it another way, we have a version of a Pythagorean identity. Secant squared x, if we subtract 1 from both sides, is the same as tan squared x. Anytime you can take two terms and make them simpler and reduce them into one term, it may be to your advantage to do that. So we're going to take that route here. We're going to replace this secant squared x minus 1 with just tan squared x. And on this side we have secant squared x plus 1. Now if you look at your answer is all in terms of sine or cos. So let's take what we have and write it in terms of sine or cos. So tan squared x, tan is just sine over cos. So tan squared x would be sine squared x over cos squared x. Secant is 1 over cos, so secant squared x would be 1 over cos squared x, and then we have plus 1. If we want to put these fractions or these terms together, we have to create a common denominator. You can write cos sine squared x over cos squared x, 1 over cos squared x. You can write 1 as just cos over cos. But we want our denominator to be squared, so cos squared x over cos squared x. And now we can write it over a common denominator, not the numerators. So we've got sine squared x over cos squared x times 1 plus cos squared x over cos squared x. And now we have two fractions that are being multiplied. Our right side is one fraction, so let's multiply these fractions and create one fraction. Sine squared x times 1 plus cos squared x. We need to use distributive property. Sine squared x times 1 is sine squared x. Sine squared x times cos squared x is sine squared x cos squared x. In our denominator, cos squared x times cos squared x, squared times squared is the exponent 4, so we've got cos to the exponent 4x. And if we look at our right side, that's where we're at. Sine squared x plus sine squared x cos squared x over cos 4x, that's exactly what we have for manipulating our left side. So what we've just done is we have proven the identity. I'm just going to write out this right side here. QED. So what strategy do we use here? Well, we used a couple. We basically put all of the tools together that we've been using in all of these examples. We factored a difference of squares. And if you see something that has a difference of squares, that's probably the trick in the identity, and I would always factor it. And if you factor it, you end up with two terms. You could have factored this again and then created 3 brackets, but it just would have made the fraction work a little bit more complicated, so I didn't do that. But if you'd taken that avenue, you could have ended up with the exact same final answer. There's more than one pathway to end up improving an identity. We didn't identify that as the Pythagorean identity, so I made that replacement. And then we had tans and secants and 1s, and our answer was in terms of sine and cos, so I just wrote it in terms of sine or cos. And then we created a common denominator so we could have 1 fraction, and then our answer was a single fraction. We had 2 fractions multiplying, so we multiplied and we ended up in the right spot. There's always something about the other side that indicates where you're going. And what indicated to me where I was going when I started with the left side was when I looked over here I had a fraction. And I had everything in terms of sine or cos. So what that tells me is at some point I'm going to have to turn everything into sine or cos, and that's likely going to be the result of a fraction. And there is one fraction that's written in terms of sine or cos, and that's tan. Tan is sine over cos. So if I can turn this into a tan somehow, then I know I've got a sine over cos, and that's how I piece together how to prove this identity. But a lot of it is just trial and error. So what I'm going to get you to do is I'm going to get you to take a shot at this last example. It's pretty tricky, but give it a shot. Check the solutions, and thanks for watching. And I'll see you in lesson 7.5.